Okay. Good evening, everyone. So, in case I'm not audible, please stop me. I didn't check my mic today. So, last day, what we did was we were talking about a finite horizon problem. And does anyone recall what type of models we were discussing? What type of RL problems? We were doing MDPs based on, that is Markov decision processes, based on what were we dealing with? We were dealing with model-based. We were dealing with model-based algorithms where the probability distribution was known. And so the reward function was also known. All these things were known to us. So we were dealing with these type of, and today also we'll be dealing with these type of models, that is model-based algorithms. This is the last of the model-based algorithms that we'll be doing. And then after this model-based algorithms, what I'll do is from next time onwards, we will go to model-free algorithms. So we are almost at the halfway stage of the course. So we have laid down the foundations of what is RL and so on. And also the assignment is out. I'll discuss the assignment after we finish the class today. So you can try. So that is around 40% of the total credits of the course. So there will be 3 assignments. I'll try to keep it 40, 40, 20 or something like that. And the first one is just model-based algorithms. We have coding and theory as well. So the model-based algorithms where all the probability distributions were known. And now, so from next day onwards, we'll be dealing with model-free algorithms. In real life, we don't know what model-free are, what the probability distributions are. So we need to estimate them on the fly as well. So what I'll try and do is do today is the only class, probably one of the few classes which I'll be doing a bit of mathematical proofs and so on. So I'll try to give you, so since it's a UG level course, I'm not going into proof of every algorithm. So that only comes in a graduate level course or a PhD level course. So but I'll give you a flavor of trying to understand how these systems, control systems and MDPs work and how you can prove convergence of these algorithms. So that's the uh, overall goal of today's presentation. So remember that we did something like this last time. So we had 3 type of problems. We had finite horizon problems where we showed the chess game and we showed that if there are fixed number, so the time is fixed or episodic time is fixed, say equal to n. Okay. So say we have n rounds of a competition like a chess tournament and so on. So that is fixed today. And we also spoke about 2 other type of algorithms, that is stochastic shortest path or episodic task, where it is finite time, but it is random. So the episode lengths are finite, less than infinity, but random. And the third type of algorithm, which you will use a similar concept, is the infinite horizon problem, where the agent never stops. And we saw that in this we need to calculate the discounted reward, isn't it? This is what we were using as the reward, or at G at time t. So we were saying that we will take all the rewards. So if you start at ST and you get reward RT plus 1, RT plus 2, and so on till infinity, so on. So you just keep adding these rewards, whatever reward you get, just add them and you weigh them by a constant gamma. Okay, so that's all we were dealing with in an infinite horizon problem. Today, what I'll do is I'll extend. So finite horizon problem, we did in details. We saw the dynamic programming algorithm. Dynamic programming we did. We proved that it is the optimal algorithm. Today we'll see another class of algorithms called the stochastic shortest path. So once you do stochastic shortest path, the infinite horizon problem is also the same actually. There's nothing different across these two except the weighing parameter and the proofs, of course, which will not be doing. So let us see what a stochastic shortest path problem means. So the stochastic, you can look at the notes on the left later on, but the bigger idea is, so there is a terminal state. Okay, so you all know that what are the components of the RL algorithm? There is states, actions, and rewards. So we know that. So there's this terminal state. So from any state I comma j, you can go to terminal state with a positive probability. That I mean, there is a path with positive probability in less than in finite steps. The positive probability to reach this in finite number of steps. Okay. And once it goes to the terminal state, it stays there, right? So this is what we define this stochastic shortest path problem to be. Is it clear to everyone? So you have a lot of states, say 1, 2, and so on, all the way to n. And they can have transitions between themselves and so on. But at the end of the day, they will reach the terminal state with a probability greater than 0. So the few properties that they have is, so number one property is, once the terminal state is reached, that is st plus 1 is equal to 0, st equal to 0 under any policy pi. So this is the policy, is 1. Okay, so that is the transition. The Markov property says that if you are in the terminal state, you stay in the terminal state. Right? So this is what it means. And there is another property which says that this is only going to hold under proper policies. The proper policies, will be using this throughout the course class today. So what does this proper policies mean? The proper policies mean that, say the probability that S2n or just Sn, here there are n states, is not equal to 0, given Sn is equal to, say, I, under any policy pi. And if you take maximum over all I equal to all the states, you start from any state. So I'm telling you, what does this mean? So you start from any state, so that's not n is 0. Start from any state I, make n transitions Okay, so if you make n transitions, it says that the probability under a proper policy, the probability of reaching the terminal state is non-zero. So the maximum probability that it is not, can you tell me what will this be? Say I define this as p pi. Can you tell me what will this be? Can you tell me an inequality for this? So under the policy pi, the maximum probability, I have already stated the condition. Under the proper policy, the probability of reaching the terminal state is non-zero. So in, of course, n steps. Any idea? So this is simple. This is just has to be this. What does this mean? 1 minus probability of Sn equal to 0 given S0 equal to I. And max of that. Max over all I. What does this mean? This has to be less than 1. Yes or no? Okay.
Yes.
So it means that this probability has to be a number, a real number between 0 and 1. That is it. All it is saying is, so if you start from state 1, even if you have a straight chain, 0, 1, 2, 3, dot, 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 n, or rather 1, 2, 3, 4, n, and 0. So there are how many transitions over here? There are 1, 2, 3, 4, and so on. So there are n transitions. Right? So this is all I'm saying. I'm saying that at most n transitions would be required to have a positive probability of reaching the terminal state. Right? So that's all we claim for proper policies. Now, so we have understood what a stochastic shortest path problem is. That is, it has n states and one terminal state. So n plus 1 states. Once it reaches the terminal state, I stay in the terminal state forever. Then there is a second probability and the third property. Property. Then the third property is it must take not more than n steps to have a positive probability of reaching the terminal state. Fine with everyone? That's it. That is the entire definition of a stochastic shortest path problem. Now, what is the goal of the problem? Can anyone tell me? So any problem, any RL problem, what will you get? So recall, every time you start from say S0, you take an action pi of S0. So we are considering deterministic policies over here because we have shown in the past that any optimal policy or any policy can have a deterministic equivalent. So for the time being, let us only consider deterministic policies that given a state S, I know the action that I'm going to select. I go to state S plus 1, S1 here, and I get a reward, right? That is S0, pi of S0. This is the notation I was using last day. S1, right? This is A0. Right? So between this is a 3-step reward function, three argument reward function. So and you go on. So I'm trying to revise stuff. So if you were not following, please try to see all these. So these would just accumulate. So S1, pi of S1, S2, and so on. So what is the end goal? The end goal is to maximize long-term reward. So what say the total reward is R, and you start. So again, the value function of S under the policy pi, what will I define this as? Tell me, what should I define this as? Say your,
Expected long-term expected
yeah,
long-term reward given status.
just all the rewards, right?
Given harm.
Summation gamma is Ri.
Yeah, gamma is also, so again, gamma equal to 1 can be set because why? Finite
Given
number of, yeah, finite number of rewards will be received. So we have seen this as in a proof that only when infinite number of rewards are there, we need to. So gamma to the power I Ri, this summation has to converge if and only if the gamma has to be less than 1, if and only if R is here n is infinite. That is, there are infinite number of steps because you can take the max of the reward and then the summation becomes r by 1 by gamma, r max. So this becomes an upper bound as we had seen before. So what I'm trying to say here is, so here we do not need that gamma, the discount factor, because we have finite number of steps. We can just put the discount factor and I will just write. You can also put the discount factor. It's not going to change anything. But here we'll just not put it because for the flavor of the question itself. So it will be Si, pi of Si, and Si plus 1. I equal to 0 to n. Limit n tends to infinity. Is this fine with everyone? So here this n is being used multiple times. Let me put m. Right? Is this clear? So n is the number of states. So I did not use n here. So as soon as you reach state S0, this will stop and every other reward will become 0. Is that fine? The terminal
Yes.
state reward is also 0, unlike a determinate state reward is also 0. So unlike we were doing it in a finite horizon problem or a stochastic or in the finite horizon problem, so we're going to keep it to 0. So this summation is the summation of all the rewards that you will ever get. So you may ask me that why did you put it to infinity? I'll just say that no worries. If once I have reached 0, I will stay in 0 and I will not get any reward. So the eventual terms from m would not actually matter, right? Yes or no? Correct. The reward is 0. So once you reach it, you can just put it to infinity. There's not going to be a problem. So now what I'm trying to say to you is, so we assume a stationary policy. That is, the policies don't change with time. That every time you sample a reward, you choose by the same policy. That is, first at time t equal to 1, t equal to 2, t equal to 3, and so on. You never change your policies. So we said the policies pi is as a same policy. That is a map and the action. That is all we are going to select. That is a deterministic map between the state and the action. Right? So that's what I have defined over here. So you can just have a look. Since it's infinity doesn't matter, which is between n minus 1 or n, really. So that's it. So now let us try to do some jugglery with these terms. So what I'll try to derive is I'll come to the Bellman operator. So I hope you remember that we did the Bellman operator in our class in the very first fifth or sixth session. So let's try to use this term and get to the Bellman operator. Again, it will be a revision for people. I'm trying to really reinforce this idea once again. So limit m tends to infinity. So for that, so what can I write this as? Can anyone tell me? First, what did I do last time as well? I did. Very simple. I know S, that is say small s 0. I know pi of S0. For the time being, I'm going to write pi of Si as AI. So this will be A0 and S1. And then I can write I equal to 1 to m, limit m tends to infinity, r of Si, AI, Si plus 1, given S0 is equal to S0. So now, anyone, how do I go about doing this? I have done this in the many a times before. What should I do? So this term again, doesn't it look like a reward again? Starting from S1. Starting from S1. This looks like the value function, yes or no?
Yes.
So yes,
So
do
all I
double
need,
expectation. And
Yes. I will just take an expectation again. I will say that S1, because I do not know S1, I will just say S1 is S prime. I'll just put a double expectation because I can always put expectations within expectations. It's not going to change anything because it's an iterated expectation. I will just condition on expected value of S1 and I'll get this. So what will I get? I will get expected value of reward S0, A0, S1 plus V of S prime. So I'll just put S0 is equal to S and S1 equal to S prime, and I'll just rewrite this equation as expected value of R of S, A, S prime, and A0 is equal to A plus V of S prime, given S naught is equal to S. So this is what I get the value function for a particular policy pi to be. And this expectation is over just the policy. Okay, and we'll see how to do this. So now tell me if I assume that pi of A given S is the policy distribution. We're not assuming any deterministic properties yet. We will come to it. Then what can I write this as? Do you recall we did something like this in the past? All we can do is we can write this as reward of S, A, S prime plus V of S prime. And I can condition on, what can I condition on? A naught is equal to, right? Yes or no? Because do you remember, we know, what do we know? We know probability of S prime given SA. Yes, this is the transition distribution. Transition probability distribution of the controlled Markov chain. Yes or no? So this is given the action and state, what is the probability of transition? What is the probability of transition to S prime? Fine. So this I know, that's why I'm conditioning with respect to A. And then I will put an expectation outside again. That is pi of with respect to pi of A given S and the inner expectation with respect to P. Yes or no? Because I conditioned on A, S was already known. So I'll just put this pi of S given A. There is one more expectation, right? Because I have to remove this conditioning, which was not there. This I introduced this artificially. Yes or no? I said that I
Yes.
also condition on the expectation. I have to take an expectation of that as well. So this is basically the summation of S prime given SA, reward of SAS prime plus VS prime. Okay. So S prime in S and then action in A of S, pi of A given S. Fine with everybody? No,
yes.
no doubts? Okay. So now, according to so this actually it's not required in this proof, but let us put the thing. So do you agree P of S is equal to 1 for, so this for pi of, for Y is equal to 1 for A equal to pi of S, 0 otherwise. So this is, I'm just overloading a notation a little bit here. So I'll just put probability P in the subscript to say that it's a probability and this is a function. Yes or no? So I'm saying that it is deterministic, right? The policy is deterministic because based on the current state, can totally determine what action I'm going to do. So for that action, I'm just going to say the probability is 1. And for the rest of all the actions in the action space, I'll say it's probability 0. Yes or no? And that is totally known by the policy pi, correct? Because pi is a function from the state space to the actions. Correct? So once I do that, what can I write the inner the summation to be? Can you tell me? Very simple. Can I write this as the probability of S prime given S comma pi of S? Correct?
Yes.
Yes or no? Because that only one term will remain. Only one term remains. Rest as 0. And R of S, pi of S, all of this, because there's only one action again, S prime plus V of S prime. That's it. So once I write this as this, I can now separate out the summations and write this as S prime given S comma pi S, the reward function pi S prime plus summation of pi of S prime given S comma pi of S into V of S prime. S prime is equal to, this is not going to change. We have already done this without the deterministic assumption as well. So there also we had seen the same thing turned out. So we're just keeping to the flavor of this question. So that's why we're not changing that. So okay, so the first term, can you tell me what is this? What is the variable only here? The variable is only S prime, yes or no? I mean, the expectation is over just S prime, correct? For S, I already know the action, right? Action is already predetermined. So if I know S, I know A, correct? I know the action for the state. Correct? And what is this? This is just the expected value, right? This is the expected value of the reward, yes or no?
Yes, it is.
S prime over the probability distribution S prime given S, comma pi. So this we have already written in the class as the one argument reward function, right? This is just R pi of S, correct? Because currently based on the, yeah, Paul,
Yes, I
tell me.
missed one thing. There was two summations. How did we get one?
So that's what I was explaining here, no? So from the outer summation, I said that the policy is deterministic policy. So for every state, I have a fixed action, yes or no?
Yes, that is
So if I
yes.
have a fixed, so then in outer summation, if it is a deterministic function, there will be only one of the n, if there are k actions, only one of them would have probability 1, right?
Yes,
Rest of them, all of them will have probability 0, correct? If one of
yes.
them, rest of them are all probability 0, so for all the other actions are just gone, right? Because it's just 0, multiplying 0 into anything.
Okay, means that this side is fully a function of S. So we know the A, and that
Yes,
is why one. Yeah.
correct,
Okay, okay, okay. Yes, yes,
correct.
yes.
So exactly that's why I'm not even taking. Even if you don't do that, it's not going to change anything. We have done that in the class before as well. It will just add one more summation and the expectation over A will be removed. So it's not going to be a problem there. So this is just one argument reward, right? This is the expected reward. Expected reward. Reward at state. Which state? Yes, correct. And the second one is just P summation of. So we will represent this as, again, it's a Markov chain. So Markov chains are represented as from state to state. So the transition probability from and to under the policy pi of S. Correct? So I'm just going to write this as P of SS prime, pi of S, S prime in all the S's, and V of, we can also write it as prime as 1 to n, right? And S prime. Correct? So I say that this probability function, this probability, so note here, note, this is all states excluding the terminal state. Because terminal state anyways is going to be V of S is 0. So we don't really need that. This is all states excluding the terminal state. So now, again, matrix form. Can anyone tell me how do I do? 1, 2, 3, dot, 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 n. 1, 2, dot, 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 n. This is P11 under the policy pi1, P12 the policy pi2, and so on. P1n pi of, sorry, pi. Correct? Yes or no? Under the current action, what is the probability that you will go to state 1, 2, 3, and so on to n? Is it clear to everybody? This is just A1. Similarly, P21, pi 2, P22, pi 2, so on. And the ijth element, j and I, is going to be, tell me, pi, state I to state j, pi of I, yes or no? And this is P of n, pi of n. Any questions? So I will write this entire matrix in form of a this in entire of a matrix, and I will say that the matrix equation is going to be V of V, where V is nothing but V1, V2, V state 1, V state 2, and so on, Vn. So the V pi of, I will just stack them in a matrix form. So I'll get V pi is equal to plus P pi into V pi. Yes or no? Correct? Any doubts? I'm waiting for your doubts, and no, don't shy away. Right? I just wrote this summation as this. So you can clearly see that V1, V2, dot, 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 Vn. P pi and V pi plus R. R is like R1, R2, Rn. And I say that is equal to V pi. That is V1 again, V1, V2. Yes or no? This is the equation. I can write this everything in condensed form of a matrix. This is the n cross n matrix. This is the n cross 1 vector, and so on. Okay. So now we come to what is called the Bellman operator.
So
Yeah.
our choice for a deterministic policy is only because of the kind of problem we are doing.
Correct. We can have a non-deterministic policy. Then also there's nothing is going to change. You will have just the summation over. So wherever you had, I'm just trying to give you another type of example. Like we have already done the non-deterministic case, so I'm just trying to do the deterministic case as well. So if you had the deterministic case, what would have non-deterministic case? What would have happened? This one would just have been the probability of pi of a given s, probability comma a, and then the reward over all actions and next states. So this is still the one argument reward function, right? We have derived this last time. So this is like, yes or no? This will be probability of s prime comma a, and you just sum over all the s primes here. So this is just the, so since you sum over all the actions and states, so you'll just get whatever was left. That is it is a random variable of s. Yes or no?
Yes.
Still one variable reward function. So it doesn't change anything. We have done that in the past, so I just made it simple, and it's just the same equation. Just the p is going to change accordingly. The entire proofs that I'll be doing is not going to be any different. The convergence proof will still be the same. Okay. So I saw V pi is equal to R pi plus P pi into V pi. So again, if I expand this equation, I can write this. Can you tell how? P pi R pi plus P pi P pi. Yes or no? P pi R pi plus P pi square V pi and so on. You can do induction, right? So it will be like p to p pi to the power I, r pi I equal to 0 to infinity, correct? Yes or no?
Yes.
So what does this mean? It means that, or not v pi, here r pi. It means that you are going, so this is p, again we have seen in Markov chain. Do you remember that p to the power I times any function? What does this return? So what does p of a distribution return, or any things like that return? It returns you the value at the ith step. That's all it returns. It's just a way to interpret things. So what you can really see is, so for example, if you recall, so we saw that probability of S1 equal to some A, some state S. We could write this as a summation of probability S1 is S given S0 is equal to I for I equal to 1 to N, and S0 equal to I. So this was like this, right? So probability of 0 to S, or rather than I to S, and you could sum over all the I's, the distributions, pi 0 distribution, right? And then I showed you that if you kept on going, you could write the nth distribution as multiple summations. That is, this is nothing but pi 0 into p, as was which was your pi 1. And similarly, you could keep on doing this for n pi's. So you can just say that, okay, pi 0 I know, pi 1 I know, so pi 2 will be the same as pi 1 times p. So I can keep going like this. So I will get pi 0 times p squared. So this is whenever you multiply this transition matrix, what do you get? Again, multiplying transition matrix gives you two-step probabilities, right? Two-step transition probabilities. I think this was all done. That's why I just recalled quickly. So the idea is,
Dada,
yeah.
one thing to ask. In the equation v pi equals to r pi plus p pi into v pi, the next v pi means on the right side, was it of state s dash? So means you took it v pi only. Means why? Because
Correct. You are right. This will be of S dash, right? This will
yes,
be, but when I am right, this is a matrix equation, yes or no?
yes.
So V pi contains all the S's, S1, S2, dot, Sn. And this product, when I'm taking the squares, are automatically characterizing for all the S primes. So that's why you're multiplying matrices and not anything, not scalars, right? So this is
Okay.
this is a matrix equation. I'm just putting the value of the matrix. This is always true. For all, this is the entire state equation, right? So if I put an S here, I will get what? R S plus summation of S prime into V pi of S dash. Yes or no? Correct?
Yes.
So now what will I do? I will just take this, and what will I do? I will write this again as R S prime plus summation of S is equal S prime equal to 1 to N P S prime S double prime V of S double prime. And I'll keep on going. And when I multiply these two, this will be just a matrix multiplication. Doesn't
Okay.
matter.
Okay. And yes, yes.
So that's why you could just replace the entire matrix. This is a vector, right? This is the left side is a vector and the right side is a matrix. The right side is also, so this P is a matrix, V is a vector. So you are just taking combinations of the columns of P. And then what you're doing is you're at the end of the day just replacing the V's once again, keeping on doing that. And once you do that, you just get n step. So the value at the ith step. So p to the power I, as you can see, is the I step transition probabilities. So basically all you are saying is what is the expected reward at the ith step if you start from the current state. And this is what you're doing is for every state you are seeing at that state what is the summation of the reward over infinity. What is the probability you will get a particular reward? What is the expected reward at time 1, 2, 3, 4, 5, and so on? Is it clear? So there are like all the steps, each of the state will have some reward, and you're just summing over that. So this is the intuition, but the math is very clear. This is the equation. So remember this equation where we only have rewards to us and the rewards are just added for every state, right? So this is just for every state, this will hold, correct?
And the one more thing, when you means in the last equation, there the last term was p pi squared into v pi. So means when you are taking
V
n
pi.
tends to infinity, yes, v pi,
V,
not r pi.
so
We
we'll
had
come to that.
r pi
So
till.
yeah, you will have a
Acha, okay, then.
p pi to the power infinity into v pi, right? You will have the last
Yes,
term.
yes, yes. Yes, yes.
But this term will go to 0, no? This will show you why. I'll show you. Don't worry. This term
Okay,
will go
fine.
to 0. This will just be a simple term. Irrespective of whatever it is, it will go to 0 because this P matrix, recall, has an eigenvalue maximum of 1, right? So I have already done this in the previous course. So if P matrix has all eigenvalues between 0 and 1, correct? The eigenvalues are between 0 and 1. What does it mean? That all the energy would be lost, like only one term, that is the one eigenvalue would remain. Rest all will be gone. And we'll see why. And this has all eigenvalues between 0 and not even 1. I'll show you why it doesn't even have. So for the time being, we'll see. For the time being, this is 0. We'll see the proof. Don't worry.
Okay.
We'll switch. Yeah. So this is, we learned that so we define a Bellman operator as T pi of V for a policy. For a policy pi, we define a Bellman operator T pi of V for a particular state. Tell me, what will you define this as? We have already derived the equation. Basically just this. This is your Bellman operator. So I will say that currently I was just deriving it for a particular value of V pi. I will say that given any value function, you give me an arbitrary value function, I will make a function or an operator in this case, T pi, which will convert this as, say, reward of S plus the summation of P of S to S prime, pi of S, V of S dash. S dash is equal to 1 to N. Correct? Again, this is for a policy pi. Is this clear? That's what we derived, yes or no? So we derived it for a policy. We derived it for pi. That is the value function pi. It was holding true. But now I say that no, it is, I will define this operator for any value. Say I define V is equal to 0, 0, 0, 0. This would still work, right? It will still work. But initially this initial equation did not work, right? Yes or no? So that in the vector form, T pi of V will be. So what can you tell me the difference between these two? What this is an operator equation which takes in, tell me what does it take in? It's an operator, right? T, what does it take in and what does it give out? And what is the difference between these two? Just to appreciate why I wrote the above term. T takes a value of a value function, right? It takes a vector V, correct? Yes or no? Because these are known to me. These are known. And it returns a what? It returns also another value function. Say V tilde. This is going to be a vector, yes or no? So this is some value in Rn to some value in Rn, correct?
Yes.
Clear? That's all it's going to do. So, but this is just a special case of that. So I just pass in V pi, then I will hold this equation. That's the idea. That's the only difference between these two. That's it. So when I just pass the value V pi, this is going to hold. Great. So this is a special case. That's it. Fine. So if we define the operator now, the same operator, and we have this. We have proved this derivation of the operator, and we'll see why it is important. Another operator I will be
Dada,
defining here.
one thing to ask, that way you said that when the policy is not pi, then we will get a different v.
V will still be the same. Pi, P pi will be different.
Acha,
No, I
okay.
didn't. Your policy is different. So this is for a policy pi. For a policy pi. And for an arbitrary V. The T pi is defined for an policy pi. But V I am just changing. Instead of putting the same value function V pi over here, I am not putting the value function V pi, I'm putting any value function. That's what we're trying to do. We'll see why I'm doing that. But is that clear? Like T pi contains all the information of the policy. And V contains none of it. Okay.
Oh, yes.
T pi contains all the information of the policy. Okay. So now I'll define. Yeah.
So T pi V pi is going to be equal to V pi, but T pi V is not necessarily equal to V, right?
Exactly. So exactly, that's what I'll prove. I didn't want to come to that. So T pi V pi is just going to be V pi. Because we have proved that this equation on the right is equal to V pi. This is a V pi is a solution for, is a fixed point for T pi. And on the numerator, T pi of V is not equal to V. That's the difference, as Antariksh is saying. But I'll show you that this is the truth. So I just didn't want to tell that, but is that clear, Atothrij? The difference.
Yeah, yes. Yes.
So this is the numerator is just like something like this. So it's like, I'll give you an example. Say f of x is just x square, right? Correct? So now I tell you what is the fixed point of this function where f of x equal to x. That is x is equal to 1 and x equal to 0. Yes or no? Correct?
Yes.
And also minus 1. No, only x 0 and 1. Correct. So what does this mean? So it means that at 0 and 1, x square is equal to x. But is x square equal to x always? Fine. Is the analogy clear? Fixed points are these.
Can you say the,
What will I say?
yes, means apart from v pi, what does any random v means? Means what is the physical significance of that? Any other v means?
I will tell you. So any other v means it's just you're giving a vector to the function and it will give you or spit out another vector. That's it. Just like this. What is the physical significance of f x equal to x square? That's the significance, right? It just gives you the square of the number. This gives, I will tell you the physical significance and then you will feel, wow, what a feel good factor. Because physical significance is you can start from any v pi, v, and reach v pi. That is the physical significance of this operator, of the Bellman operator. And that's what is the plan for the subsequent 1 hour. Okay.
Yes. Yes.
Because you have no idea of v pi, right? But you can randomly choose any v. That's why the entire thing comes out. Okay, now the Bellman optimality equation. Very fast, let us derive this. The optimality equation. Tell me how, first let us define the fixed point equation, and then we'll define the optimality equation in the same way. So what was our optimality? So say we said the optimal function or anything that we want to be optimal, say V star of S was defined as the maximum over all action Q of S comma A, yes or no? For any function or whatever you are writing, Q star or whatever. Fine. If this is the optimal Q value function. Right? You choose the action that maximizes the value function of the state, right? That's how we defined. Any questions? Okay. You remember? No, this is what? Now, okay, even if you don't remember, let's try to do this. This is, again, I will write down the inner summation as the same thing. S A S prime plus V S prime, given S is equal to S not equal to S, and action is equal to A. This is what our Q value function is. This is the total reward. Total reward. Yes or no?
Yes.
And you say it's maximized over all actions. So I say that what is the maximum reward? What is the reward, expected reward given the state and action? That's it. So now let us write this down. So max of A given AS. Tell me what will this be? Summation over S prime. Tell me. This is reward of S A S prime plus V of S prime. Probability of S prime given S and A. Correct? Any questions? Any doubts? Because this is known to me. Fine. Okay. So this is fine. This can be again written as summation over S prime R of S A S prime S prime S A plus summation of probability of S to S prime for, so I'm writing this again as S to S prime under the action A, V of S prime. Tell me what will be the first term? What will it be a random variable of? The first term is just summing over S prime. So what are the other random variables remaining? So this is
But
S and A. Yeah.
but if the policy is deterministic, then only yes.
Exactly my point. The policy is not deterministic here. Just see why. Because the policy is not known to us. We are selecting the policy, right? Action is being selected means the policy is being selected.
We are trying to find the optimal first.
Yes, very good. So we are trying to find the expected value given S prime. S prime from some distribution S comma A. This is what we have done in the first few classes as the two-step reward argument, right? Two argument reward function. Two argument reward. That under the state and action, what is the reward I'll get on average? So this is R of S comma A plus summation of S prime from 1 to N is S prime A Bs prime. Again, very simple, correct? So this is exactly the same equation that I'm going to write. And this is I'll be defining as, so this is for the, again, this is for the optimal policy. I just put a star everywhere, star, star, and so on. This is for the optimal policy. But I say that again, I'll define an operator. The operator is the Bellman optimality operator. Optimality operator. which will be defined as for a particular state S. It is the maximum over all actions in the state R of S comma A plus summation of all the states remaining V of SS prime A V of S. Correct? So this is how I define the Bellman optimality operator. So some books will just define it. So I just came to the reason why we define it this way. Fine. The algorithms will make it clear why it is defined this way. Just basically the optimality, the equations that hold for equality, the fixed point equation, you're just replacing the value that makes it equality with any other value and make it a function, basically. Okay. So now let us interpret one of these. So I will interpret t pi to the power kv, and you can interpret the tk to the power v as your homework. What does this mean? As your homework and upload it. It's the same thing actually, but doesn't really matter. So let us try to interpret the first one. T to the power k v. Small. So first tell me, what does t, how can I write this as? Can I write this as t pi to the power k minus 1 into t pi v? Yes or no? Because this is a function at the end of the day. Correct? It's a map, right? It's a affine transformation at the end of the day. It's just an addition of a vector and multiplying with a matrix. Correct? So t to the power k means n times I'm applying the same operator, basically. So now tell me, or basically I can write this as t pi to the power k minus 1 of v into t pi. So now tell me, what is this equivalent to? So t pi, again recall, t pi v is defined as r pi plus p pi into v. So now tell me, what will I write this as? So this is the vector that I'm now inputting, right? This is the beauty. See, now this t pi operator takes in another vector. Say you can take this vector vk minus 1. Name this vk minus 1, but this is a vector, different vector, right?
Yes, we are gonna write r pi plus p pi vk minus 1 or p
Correct.
pi c to t pi k to the power, sorry, t pi to the power k minus 1 v.
T pi to the power k minus 1 v. Yes or no? I just put, this is your elementary algebra, class 6 algebra. I just put the value of the function wherever it has to be put in the place of v. Right? So now again, by induction, I can write this as t r pi plus p pi of t pi of rather than r pi of t pi of k minus 2 v pi. Am I writing it correctly? R pi? No. P pi. Yes? Fine? Good. This is r pi plus p pi r pi plus p pi t pi k minus 2v. And I keep doing this. What do I get? I get r pi plus r p pi r pi plus p pi square r pi dot 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 p pi to the power. Tell me. So initially, how much? How many times would I
K
have to
minus 1.
divide? Yes.
p pi power k
K
into p pi power 0 it will be then if or
to v. Yeah.
uh-huh.
Right. So t pi will become 0. T pi to the power 0 is just identity matrix, identity operator. That's how we define this. So this is just going to be all the terms that you are going to sum over. And then you have, so you can define v0 as say all zeros. And then you can just put this to 0. If you do that, what does it going to give you? It is going to give you k step rewards, right? K step reward. So it's like reward at step 1 reward, step 2 reward, and so on. That's all. Very nice. Great. So we have understood what does this operator mean. So anytime, as Antariksh was telling me, anytime you apply this operator, you take one step and see, observe what the reward is. That's all you are going to do under a given policy. That's all you want to do. Okay, so now I will define two lemmas for this operator, and then I'll go to the proof, which will be the last thing we do. These are now applying these operators, just making you familiar how to use this operator. So now I tell you the first lemma is the monotonicity lemma, which says that if the value that I give into the operator is greater at every value, at every input, then after applying the operator also, it's going to remain the same. So I'll prove it for this. Prove for and this will be a homework. I'm just doing the alternate one so that you can have flavor of both. Right? So let's try and do this. So I will try to do. I will say that t to the power kv for the optimality equation. Optimality equation is less than t to the power k v prime if v less than v prime. What does v less than v prime mean? So if say v I input as 1, 2, 3, 4, v prime must be 5, like 2, 3, 4, 5. That for every state, the corresponding value should be greater, correct? Or than equal to. You can also put 4. Right? Clear to everyone? So let us try to see what TV of S means. Tell me what TV of S means for a state S. The optimality equation. Yeah, tell.
R pi plus d pi times v of s again.
So there is no, so R pi is what you're trying to select, right? So this is the optimality equation. So there is no policy as such. Right? So you can clearly see there is no policy in this equation because you are selecting the policy, right? You're selecting the action that maximizes the reward, correct? So I'm doing the optimality equation here. So this is just this, right? S prime equal to 1 to n E of S prime for that action into V of S prime, correct? Fine. Now what do I do? Very simple step. What do I do? Do you agree V of S prime, V dash of S prime is given to me? Right? That's how I stopped. That's why I started. For every S, V of S is less than V prime of S. Okay. So I can just replace this as an inequality, right? I'm just replacing every term with a term greater than it. So the max, so this term has to be greater, right? Because all these terms are positive.
Yes.
This is positive. The probabilities are positive. So therefore, I can clearly replace a term with greater term and greater inequality. S prime and therefore, not since therefore. Now, what does this mean? See the flexibility now. This is what?
I can replace it with dv v prime of s.
Very good. So clearly, what does it mean? If I input a value function which is greater, then the optimality operator will always give me a value which is greater. So now I can keep applying on both sides induction. So T of, so again, by monotonicity, I will use monotonicity again from equation 1. So it's just T square V less than equal to T square V dash. Yes or no? and so on, k times. Any questions? Use monotonicity recursively. Okay, so this is one of the proofs of monotonicity. You give a higher value, your optimality equation will keep on giving you a higher value compared to the other. One is, so if you have a constant, then you're upper bounded by this value, and so again this is with and without value of pi. So I will do with value of pi now for this, and I'll leave the without the value of pi for you as homework. So let's try and do this. So the
Can
E
I
here
ask a
is,
question?
yeah, sure.
Yeah, I think it might be a bit silly, but uh,
Go ahead.
the reward function, it's not necessarily going to be greater than zero always, is it? Like R of
It
S P.
does not have to be.
Uh, but then will the inequality hold?
But the probabilities are no, this is not being multiplied with anything.
Definitely, the probabilities are gonna be,
Positive, right?
yeah, they would.
The probabilities are positive. So if you're multiplying positive numbers and you are, so these are greater than zero. So if I, so
Right,
let,
sorry.
don't worry. Let me just write it down. So let's say AI xi, right? Just this is just some constant, some c, doesn't matter. So AI xi is given to me and AIs are greater than zero. So if I tell you yi is greater than xi, so I can clearly say that I can write yi. I will write it down. Let us prove it. It's not, if you're not getting it, let's prove it. So this yi is xi. So I will just multiply ai on both sides. It's a positive number. Similarly for all i's. And I'll just sum it, right? Correct?
Yes, it's okay.
Yeah. So now let us try to do the other proof. That is t pi of v plus re to the power k is less than equal to, again there are many k's over here, so just please bear with me. Let's put gamma t plus gamma e is less than equal to t pi kv plus gamma. Let's see how does this go about. So for any state is, okay. So now what is first, again step one is to define, use the definition. What is t pi of v plus gamma times e? And this is gamma greater than zero. This inequality will flip for gamma greater than zero. Gamma less than zero flips. We'll see why. So tell me, what can I write this as?
So that is gamma E, V plus
Yes,
gamma.
E is a vector of all ones. I wrote it down. I forgot to mention all ones. Okay. So I basically add E to gamma to every V, right? So V plus gamma E for a state S means Vs plus gamma, right? Clear? No, no problem.
Yes.
So now what can I write this as? Tell me.
I can just write it as R pi of
Okay,
SA plus P pi.
just
V-
S,
Yeah,
not
sorry.
A. R pi of S and P pi of,
Just for optimality. So, yeah, P
yeah,
pi V plus gamma of S.
yeah, of that state is. Now let us write it in the full expanded form and then see it. So this is for state S. So this thing I can write this as summation of S prime is equal to 1 to N P of SS prime V plus gamma E, correct?
Yeah, But I
Or
guess the more intuitive way to think about it is by thinking of it as matrix multiplications only, because for like each row,
yeah,
like
yeah,
the sum would be equal to 1, I know, and because E is the vector of all ones, so
very
I
good.
know that it's
Very
going
good.
to be E only.
Exactly.
So
But then you would have had an equality. There is an inequality here. You're absolutely on the right track. When I saw this equation for the first time, I asked my teacher that then as well. But why do I see a inequality? It should be a equality, right? Show you why. So summation of S prime, I'll just expand this PSS prime. But it doesn't make any difference. It's the same equation. Intuitively also it's the same. Okay. PS. Okay. And then I have a summation over is equal to 1 to n gamma P of SS prime. Is this step clear? First tell me. Then I will tell you what. So this thing, do you agree, is TV, correct? T pi of V. Yes or no? Fine. Any questions? This is T pi of V by definition, right? Clearly, I can
yeah,
see the
no problem.
definition. Yeah. And this second term is I am going to debate that it is less than gamma. Why? Look at this term. St plus 1 is equal to S prime, given St equal to S and pi of S. And you're summing over S prime equal to 1 to n. That is nothing but equal to 1 minus probability of St plus 1 equal to 0. No, we had not accounted for the terminal state. Not accounted for terminal state. This is less than 1. Correct? Fine with everybody? Okay. So this will be
Yes.
TV gamma E of S is less than equal to P pi of V plus gamma for that state is. And you can keep doing this and it will be like K gamma at the end of the day. If you have T to the power K. And you can just put K here. So this is by induction also, this is going to hold. It's not going to be a problem. For every K, this is going to hold. This is independent. Okay. So you try to do it for the other case where you are using the Bellman optimality equation. So this is what's just to make you understand and have the flavor of the optimality or the Bellman operators. Now we'll come to the crux of the discussion. That is proving that policy evaluation algorithm we discussed long back. You remember the policy evaluation algorithm? We did it using our grid world example also. What was the policy evaluation algorithm? I start from V pi, use Bellman equation, or start from V0, Bellman equation. I get V1, Bellman equation, V2, and dot, dot, dot. I had said that it converges to V pi, right? If I keep using the Bellman equation iteratively, that's what
Yes.
your algorithm was. So basically, we were just writing your, so just recall your Bellman equation, in your policy evaluation algorithm for a state S was just this. Action in AS, pi of A given S, summation of S R, yeah, S A, sorry, R plus gamma times V of S prime. This is all we were doing. And we were telling, do it continuously, use the Bellman equation iteratively. And you will get at k tends to infinity, V pi, K pi, Vk tends to V pi, right? This is what we had said,
Yeah,
isn't it?
first we were trying to use the optimality equation and say that we would choose the optimal V pi after every step, but then we showed that no, we don't need to do that. We can just
Correct.
do it iteratively, and at some
Correct.
point we would just reach the
Yeah.
optimum.
So here we are not even doing an optimal equation. Here we are trying to find out the value function of a policy. Optimality was policy improvement, where we, for every improvement, we took a argmax as well. And this is just evaluation, finding the v pi. Because v pi also we don't know. We just know the policy, right? And we know the p probability. We know known is the probability distribution, prime SA, and the reward function. These two are known. Rest are not known to me at all. But I want to know v pi. I said that you randomly select v0 to be something, and you just use the Bellman equation for. So this is the Bellman equation for a policy pi, right? It is not the optimality equation. Optimality equation also you can prove the same way. Clear, Antariksh? And then we did the value iteration, which will be your homework as well. Is it clear? Any doubts? I'm happy to.
No, no.
Okay. So now we have simplified this entire equation to what? We have said that, say you start from V, so V naught, and I initialize V naught. And I can say this entire big equation I wrote so nicely, I can write it in one line as T pi of V K plus 1. Yes or no? This I can write just in one line. This entire equation. Now,
Yeah.
Antrich, is the physical significance of the reason of defining this operator clear to you? Hello?
Like this shows up
Yes.
often
Yeah.
in the RL algorithms where we know the policy and where the state changes that, and we can't always write the Bellman equation again and again and again. So it
Yeah. All the
this
proofs
is
can be done in a simple way. Exactly. So the entire operator, entire thing that we wrote, which was so complicated, if you just expanded the terms one after the other, it would be looking like a nightmare. So that entire thing, the policy evaluation, has been, until convergence, has been concised into this one operator equation. That's the beauty. Now let us try to see that. What did I say? As k tends to infinity, vk tends to v pi. That's what I have to prove, right? Fine.
That is starting from any V.
Any v naught says you can start. So I can write this as what? I can write this as t pi. Vk can be written as t pi of vk minus 1, and so on. So you can write this as t pi to the power of k plus 1 into v naught. Yes or no? That's what you can write this as, or just vk as this. Correct? By induction. Fine. So what I say is limit k tends to infinity, t pi of k for any v is equal to v pi. This is all I have to prove. Okay, for all v. Now, I think we are good to go. We can first start from the very definition. First, tell me t pi to the power k of v. We have already analyzed this. Let's try to expand this simply. So t pi of k to the power v, do you agree can be written as? Yes or no?
yes.
This is what I have to prove. This is the policy evaluation algorithm. Very good. So I will write this as yes or no. Very simple, two steps. Again, I can write this as
R
P
pi
pi.
P3 R pi plus P pi square Tk minus 2.
Good, very good. So I can write this as R pi plus P pi R pi plus P pi square T to the k to the power minus 2 and B. Now I go on all the way till 0 and I write P pi to the power I R pi I equal to 0 to k minus 1, and I will have plus P pi to the power of k V. Yes or no? Am I right? Right? This is because here I'll get t to t k to the power 0 and V. Correct? Yes or no? This term just goes
Yes.
on decreasing. That's that one more term if I write it will be easy to understand. P pi R pi plus P square R pi plus P to the power 3 t k minus 3V. So now I have this equation, very nice equation I have, which is t to the power kv for the policy pi is the summation of I equal to 0 to k minus 1 p pi to the power I r pi plus p pi to the power of kv. So now, O3, this was the question that you had. What happened to this term, right? We had already written. So I will take limit k tends to 0 for infinity first. And my claim is for limit k tends to infinity, p pi to the power kv is equal to 0. Can anyone help me to prove this? And any idea how to do this? The hint is use the property for proper policies. Policies which I defined long back. What did I define P proper policy to be? P of Sn not equal to 0, given as 0 is equal to I, for the policy pi is less than 1. Max of all 1 to n. Right? That is proper policy reaching terminal state. Terminal state in n moves. Right? Okay, so now I have to use this to prove p pi to the power kv equal to 0. Okay, so not evidently clear, but if I give you one special case, say m is equal to, or let's start with 2n. What would be probability of S2n not equal to 0 given S0 equal to I, comma pi?
It not be like 0 because like we had stated that in steps it has to reach
No,
the terminals.
does not have to reach terminate. Saying less than 1, it means it can be still greater than 0, not reaching. So look at this equation. This equation, what does it say? The probability of not reaching. So this, what is the numerator here? What is the probability what you're trying to find? The probability of not reaching state 0. That is a terminal state, right? Correct?
Yes.
Given any state is less than 1, which means 1 minus probability of Sn equal to 0 is 0 equal to I, comma pi is less than 1, which means probability of Sn equal to 0 is 0 equal to I, given pi is less greater than 0, right? Which just means greater than 0. It can be any number between 0 and 1. Correct? If it is 1, then it will be 0. But if it is not 1, it will be some positive probability, yes or no?
Yes.
That is like, say if the probability is 30%. So in n terms, 30% of the times you will finish, or you will require more times. Like on expectation, you will require 1 by 0.3 times. Correct? Yes or no? That's the idea. Okay. So can I write this as probability of S2n not equal to 0 and probability of Sn not equal to 0 given S0 equal to I, phi. Are these two equations same? Are they equal? And if they are
It
equal,
should
why they are
be
equal?
because
Yeah,
if Sn is if any term between them it becomes zero, then I won't be able to move to any other state from that terminal state.
correct. So if Sn is 0, it means that S2n has to be 0. So since I have to find the probability not equal to 0, Sn has to be not equal to 0, which means if you negate both of these, not, that is Sn, S2n, the simple logic means that Sn not equal to 0. First order logic. This is probability of S2n equal to 0, not equal to 0, given Sn equal to 0, S0 equal to I, phi, probability of Sn not equal to 0, given S0. So this is just the base rule, the conditional probability rule I'm using one after the other. So now by Markov property, if a later event is known, it is independent of any past event, right? So try this as your homework. I want a discussion on this in the group. What did we discuss in the Markov property? St is 0. It's an interesting question. I could do it in the class, but it's good to think about it. Is St given St, right? This is the Markov property. But I want you to see is, we know this, but I want you to prove is St plus 1 given S, say L, SL minus 1 dot 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 S0, where L is less than T plus 1 is just equal to St plus 1 given L. That is, there could be L could be something like this. And there could be L plus 1, L plus 2, L plus K, and then T plus 1 may come. There could be a bunch of terms in between, but the last term between, that is the most recent term, determines the most recent term in history determines the current state. This is what you have to prove also in Markov property. It's exactly the same thing because you have to just use Bayes rule again once again and just prove it. Try it out. So this I can write this as S2n not equal to 0, Sn not equal to 0, and pi. Probability Sn not equal to 0 given S0 equal to I, pi. Correct. So now, do you agree this is same as this? So this will be upper bounded by p pi and this will be upper bounded by p pi. Because the maximum is the value given to me. P pi is the maximum of all these. Correct? Yes or no? P pi, the probability is maximum for all of the probabilities starting from any state. So I will get this is less than p pi square. Any questions? Questions? So I just broke it up into two summations. This is clear. What is, is this clear? That n and 2n, the difference is still the same of n places as it is the same for 0 and n. This is called stationarity. Stationary. Because the policy pi is stationary. It doesn't change. So the Markov transition probability P is also stationary. So it is not changing with time. So basically n steps is same as starting at n or starting at 0. Yes or no? Fine. Okay. So by induction, can you tell me what would S2 Mn be if m is equal to some multiplication k into n? Not equal to 0 given S0 equal to I. And tell me. m is some integer, that is, if m is some integer that is a multiple of n, then can you tell me what would this probability be? For 2n, I saw it was p pi square. For mn, it will be less than equal to, by induction, p pi to the power n. Yes, by induction. So now for any arbitrary k, pk or sk not equal to 0, s0 equal to I, comma pi, can you tell me what can I write this as? K can be any number, something like this, right? Some q times n plus some remainder, correct? Right? Yes or no? K is any number, so it may not be an exact, may not exactly divide n. For example, n can be 2 or n can be 4 and k can be 15. So it will be like q will be 3. So it's just a division, long division. Okay, so I will write this as what?
But even then it would be less than p pi to the power q.
Very good. Just see why. So I will write this as p pi. So I will write this as two terms here. Probability of sk qn not equal to 0 given s of 0 not equal to I into pi into probability of s k not equal to 0 given sq not equal to 0 and pi. So this has to be less than equal to 1, right? 1 is still greater than this. A probability can never be greater than 1. So I will replace this term as 1 and all this term as just p to the power of p pi to the power q. So basically you can say that this is upper bounded by what? K by n. Yes or no? Fine. This is a perfect square, so I just put this value here, and this is just the float term. So if this is 14, it is essentially p pi to the power 3. You have an upper bound like that, basically, right? Okay, I will just write this down once again. Sk not equal to 0 also means sqn not equal to 0. S0 is equal to I comma pi, which is same as probability of sk not equal to 0, sqn not equal to 0, s0 equal to I pi into probability of sqn qn not equal to 0 given s0 equal to I comma pi. Right? And this term we have already seen is p pi to the power q, and this term we have seen is less than equal to 1. That's what I have done. So now it is very clear, right? So once I get this term, so I will just put a dagger or some equation here. So star from star, what will I write? This term p pi to the power kv can be written as, tell me, for every s, what can I write this as? First of all, tell me what is p pi to the power k vs means. I have already discussed it. This is summation of s prime in s, or rather 1 to n. Just if you're not following, please let me know. I'm just writing out the. So this is sk equal to whichever state you are going to go. S prime given S0 is equal to S under the policy pi into V of S prime. Yes or no? This is K step transition. Yes or no? This is K step transition. This is clear? That's what I
Yeah.
wrote. If this is the K step transition, I just wrote the entire probability as a k-step probability. So now this one I have shown to be less than equal to p to the power of k by n. Yes or no? I can just take the maximum out, maximum of s prime. I'll just not be shabby, and I will write down the maximum of s prime, bs prime, and summation over p to the power of p pi to the power of k by n. Right? 1 to n. Do you agree each of these terms was 0? As limit n tends to infinity, k tends to infinity. This is 0, right? Tell me why it is 0. If you're following. This is 0. Why is it 0? What is p to the power k? P pi is less than 1. So any number less than 1, if you put it to infinity, it will go to 0. Yes or no?
Yes.
So this is just going to go to 0. This is why what I was going to prove, as I told to Othridge. So this is going to totally to 0. So now I will get this equation. Limit k tends to infinity. E to the power kv is summation of limit k tends to infinity, I equal to 0 to k minus 1. What else? P pi to the power I r pi. Now tell me, what is this? I have already defined this once. This is equal to
tk minus 1.
V pi. Just see, I have defined this. See, where is it? Yeah, there you go. There you go. Yes or no? For all the values of pi, I told the other term will go to 0. This is just v pi. Yes or no? Fine. From dagger. I've already proved this, so I can just say it is equal to v pi. Okay. So this is the first proof is done. That is, at t tends to k tends to infinity, this is going to converge to v pi. Very good. Now I have to prove that v pi is a fixed point and a unique fixed point. That is unique solution. How do I prove it? Can anyone tell me? I have to prove that. So I have proved first thing I proved is what? Limit k tends to infinity for any v for all v is equal to v pi. This is what I have proved. Now, second thing I have to prove is I have to prove t pi equal to v pi. Can you tell me how can I prove this? Instead of if I just using the operator statistics, the operator data. So I can just say tk plus 1v is equal to t of to the power kv. Yes or no? Right? Okay.
Okay, and then you will put limit in both sides.
Very good. Limit k tends to infinity. I will just put t outside, t to the power. It's a finite func operation. It's bounded, so I can take the limit inside. This is v pi. And I can write this as v pi again. So t v pi. So this is one solution that it is that v equal to v pi is a solution to the operator, to the Bellman operator. But it does not prove that it's a unique operator. Can you tell me how I prove uniqueness? Unique. So the third thing is uniqueness. How do I prove uniqueness? For uniqueness, v equal to v pi, right? if I say the uniqueness, say
I think
there
we
is
should go by contradictions that like let's
correct.
say there's another vector
Yes,
that's
very good. So let there exist a V such that T pi V equal to V. Right? Very good. I am happy. So I will just take a square on both sides now. I'll put T pi. I'll make a T pi on both sides. I'll get V. Okay. I will get T pi squared V is equal to T pi V equal to V. And I will keep on applying this. Right? This is already from just because I have this equation of fixed point, I can keep on applying the function again and again. So I will get T pi to the power kv is equal to T pi to the power k minus 1v dot 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 is equal to V. Correct? Any doubts? And I go on and I put limit k tends to infinity, and I have shown that that is equal to V pi. So clearly I see V pi equal to V. Right? So these things we saw that like what are we actually gaining? We get a unique solution. We get unique convergent solution for all these Bellman equations. Okay, so now the other equation that we other thing that we do, and we will not do in interest of time and interest itself, is that if we keep on iteratively using so this is the value iteration algorithm, which says that keep on repeatedly using the optimality equation, that is the optimality operator, you will get the optimal policy, optimal value function. This is the other equation on which we solved a lot of questions, and so you're part of your implementation homework, which is value iteration algorithm. You keep on using the optimality equation, you will get the optimal policy. Now I will end, since I did not do the proof for the optimal equations, so I will do a couple of what do you say, ways to solve for it, right? So one is Gauss-Seidel approach, right? So recall for V star, if you use this policy V k plus 1 as TV, right? Do you agree? I'm using the optimality equation, yes or no? So this is basically max of all policies in AS, Vk plus 1 of S is, help me out, S comma A summation of probability of SS prime for that policy A and V of S prime. Yes or no? Correct? No problem?
Yes.
This is Vk of S prime. Okay. So now I tell you that all this while what I was doing, I had a V, right? I had a V for 1, 2, and I had n values. This is k plus 1, and this is Vk. Again, 1, 2, n. So for every update of a state I was using every other value from k minus 1, yes or no? And I was maintaining two vectors, correct? And finally, when I completed all the steps for I equal to 1 to n, I was using k minus 1th estimate always. So now I tell you, I don't use the k minus 1th estimate. I do an in place update. That is, for the ith update, I will use these values to update it, and the previous states, these values to update this. Do you agree? Fine. Okay.
yes.
So we define another operator called say F operator, which is something like this. k plus 1 is p of, so this is the Gauss-Seidel operator will be f of k plus 1 s is equal to f of vk of s. So now can you help me write down this? So the idea is for a current state I, let me write down the idea for a current state I, use the vk plus 1 j for all j less than I and vk of j for all j greater than equal to I. Fine. That is, I'm going to shade this out. Fine. To update this current state I. So now let me tell me how will I do that? So I can define an operator again. AF will be defined as R of S comma A plus summation of S prime equal to 1 to, tell me, I minus 1, or so here S minus 1 up to S minus 1. Which state am I going to use? Vk plus 1, yes or no? Agreed?
Yes.
Vk plus 1 S prime, and from S prime equal to I or small s to n, I will use the previous state's S prime. So now this Vk plus 1, I will replace this as f Vk S prime. Fine. So where the base case is, can you tell me what is the base case? 1 is equal to T of V1. Yes or no? For the first case, you keep the initial thing where you use everything here. And for everything other than that, Vk plus 1 will be updated as f of Vk. Yes or no? Fine.
Yeah.
Very good. So this is called the Gauss-Seidel. Like anywhere you use you keep on using in place updates, it's called a Gauss-Seidel. When you implement this algorithm yourself, try the Gauss-Seidel version also. It's not a part of your homework, but try the Gauss-Seidel version, or you can just use the Gauss-Seidel version, which will give you a faster convergence in place updates. And in asynchronous value iteration, what you do is you select any arbitrary, I'll just write it down here and not arbitrary state S and update it. Any set of arbitrary set, it can be a set, it can be list. So that is why it's called asynchronous. So you say, I'll just, okay, asynchronous update. Say I select a state S dash, which is say state 1, state 5, dot some, which is a subset of the entire state space. So what I do is I use this update for all the states in S tilde and keep the rest unchanged. Right? Clear to everybody? Clear? Right? Any questions? So what am I doing is between all the states, I select a subset of states, apply the optimality equation. And I get the updated value of Vk plus 1. And when I go to k tends to infinity, k tends to infinity, Vk plus Vk tends to V star. Okay. So clear to everyone? If it is clear, so I'll just stop here. because that ends our model-based methods. I'll show you the assignment. I have uploaded the assignment. The assignment has around only 6 questions or 5 questions. Just 5 questions, 8 points each. So we have a question on Markov chains, which was also there in your homework. So if you have done it, it will be fine. So if you have done it, it is fine. So you will get this Markov chain equation. I have a updated bandits problem for you. It's a new bandits problem. Simple only. I have a MDP based problem. A fun question you can try, a betting question. And then I have 2 programs. One is a policy gradient based approach for the same code that I used for doing a UCB and epsilon greedy algorithms. And I have a value iteration algorithm for you to implement on the same Python file that you implemented Q-learning and policy improvement on. So that is it's due in a month time. Have time, take some time out and solve it. It will be around 40 points. So I'll give 2 such assignments more and we'll be done. Okay. So if you have no more questions, I'll stop recording. Thank you. Okay.